So in this screencast we're going to see some operations in CoCoA-5 relating to power products, polynomial rings and ring homomorphisms. Some of these we've already seen, but I think it won't do any harm to have a quick reminder. So I'll assume that you've already got some basic familiarity with CoCoA, for example seen what we did effectively yesterday. So let's go straight in, and the first thing I want to deal with are power products. Remember, well, we'll see what those are in just a moment. I won't recall the full definition. So the main point here is that CoCoA-5 itself has no special type for representing power products. They're simply represented as ring elements in polynomial rings, in other words as polynomials, with leading coefficient equal to 1 and exactly one term. But otherwise CoCoA-5 has no special way of representing them. It's not distinct from a polynomial. We see in CoCoA-Lib later on that there is a distinct representation. So let's have a look at some functions especially to do with power products, especially for them or producing them and so on. So we'll actually start with a particular example. So we'll start with this polynomial ring here. So I'll send that to CoCoA. Right, now down here at the bottom. So I'm going to define, well, two polynomials, t and t2. Now in fact these are power products because, as we just seen, they have leading coefficient 1, they have exactly one term in them. So we send those two over. Now what's special here, we can't do this in general with polynomials, but since these two are recognized as being power products, we can compare them with a less than operation, and this comparison uses the term ordering of the polynomial ring. So in this particular case we see that x cubed z squared is not less than yz. So that's one special operation we can do with power products. Another one we can do is we have a sort of inspector. We can take a power product apart and get its exponents from using the function exponents of t. So in this case, so if we have a quick look here, we see that at first glance it seems the exponents are just 3 and 2, but we have to bear in mind that this is really x cubed times y to the power 0 times z squared. So we have 3 indeterminates, x, y and z, in that order. And so the exponent vector is going to be of length 3, corresponding to x, y and z. So the exponents are indeed x cubed y to the power 0 z squared. A sort of inverse to this is the function make term. We can see it here. Now with make term we have to specify the exponent vector and the polynomial ring we want to use. So in this case, if we say take the exponent vector 0, 5 and 1, that's x to the power 0 times y to the power 5 times z to the power 1, in other words y to the 5th times z. So that's a sort of inverse for exponents. So here are some more useful functions. One we've already seen is LPP. We can apply that to any polynomial. Of course, if we give it something that's already a power product, LPP doesn't change anything at all. Another special case for power products is the radical function. The radical function for a power product simply takes all those is a product of all indeterminates that divide the power product. If you like, we take all exponents that are positive and we simply set them equal to 1 rather than the values they have before. So we see here, for example, that the radical of x cubed z squared is just x times z. Is divisible. I think we can guess what that is. The only thing you have to be slightly careful about is which way round do the arguments work. So this is t divisible by t2? In this case it's not. Well, number of terms, this is one way we can recognize when we have partly recognize where we have a power product. Number of terms is of course 1 because, as I said before, it's actually viewed as a polynomial. And the support, So the support of a polynomial, we've seen that before, and that actually gives me a list of, well, it's a list of power products, but since they're represented in CoCoA-5 as polynomials, so these are all polynomials. In particular, this last one, the 1 here, is not an integer, but it's actually a polynomial. So it'll be 1 times x to the power 0 times y to the power 0 times z to the power 0, although it prints out the same as an integer. Just a quick note here to contrast LPP, the leading power product, and Ln, the leading monomial, that takes into consideration the coefficient. So we have, for example, the leading monomial of t in this case, which is we already know is a power product. The result here is then, in fact, also going to be a power product again because the coefficient is 1. But leading monomial retains the coefficient in there, so the coefficient appears in the result. And so, in general, the leading monomial of a polynomial is not going to be a power product. It would be if and only if the coefficient is 1. So we have a couple of exercises down here. So one's pretty easy, just write a CoCoA-5 function which says whether its argument is a power product or not. I'll leave it up to you to decide whether you want to do full safety checking on the one argument that it's passed or not. This one's quite a bit trickier. If you've already done a little bit of studying about term orderings on power products or PP orderings, then you could consider doing this. If you've not studied them, then this one is probably too hard for you. Or you can look in a book by Robiano and Kreutzer, where they work through a number of properties of term orderings. This is actually based on a result proved by Robiano many years ago. A couple of exercises there. Polynomial rings, in fact we've already seen this before. Once again, I'll emphasize the use of this double colon equals operator. We use that when introducing new indeterminates on the right-hand side. So we have 4 examples here. And I tend to use the name P for a polynomial ring. So I created 4 polynomial rings here. I think they should all be fairly easy to read. This one here, the ring of coefficients is Z modulo 31, which happens to be a field, because 31 is prime. We'll also notice that we can have indeterminates whose names are longer than single letters, like alpha and beta. And here we've specified the Lex ordering. That we've already seen as well. P3 and P4 at first glance appear to be identical. In some sense they are. It's the same polynomial ring and the same term ordering, but when we create them in CoCoA, CoCoA doesn't check to see if a ring like this one has already been created. It simply creates a new one. So they'll have different ring IDs, and as far as CoCoA is concerned, they're different rings. So let's read these into CoCoA. So I've read the 4 definitions in. So is the ring P3 equal to the ring P4? According to CoCoA, it is not. So as far as CoCoA is concerned, they're not the same ring, even though all their properties are the same. So just be a little bit aware of that. So try not to recreate a ring if you've already created it once. Try to get it out of some datum that you already have, like ring using the ring of function or some other way. So here are some inspector functions for polynomial rings. So we have coefficient ring that we've already seen before. Number of indeterminates. The indeterminates as a list. We can also get indeterminates one at a time. It's indet, the ring, and then the index. And this is effectively just getting the nth element out of the list before. So the first indeterminate is, in this case, would be x. There's a similar function inside CoCoA-Lib, and there we have to remember that indices start at 0 rather than 1. Here's a new one we haven't seen before, and it's the order mat. So it turns out all terminal orderings in CoCoA can be represented as square matrices with integer entries. And this gives a matrix that defines the term ordering in the polynomial ring. So This is a bit strange. So ord mat for P, I don't actually... Oh, I think P maybe was defined earlier on. Well, I'll take P1. We'll send that to CoCoA. And so what we see here, for example, this is a matrix that represents the Degrev-Lex term ordering for 4 indeterminates. So once again, this will make sense if you've already studied a little bit term orderings. If not, you'll have to look it up. We're not going to cover it here. Some more functions. So these ones are testing properties of the ring. So is P3 a polynomial ring? So the definition should be fairly obvious. Is it a field? No. Is the coefficient ring of P3 a field? No. What about P2? That was a Z modulo 31. Is that a field? Yes. And something else I actually forgot to put in is the characteristic. That applies to any ring. So we can ask for the characteristic. So we've got ways of creating polynomial rings, or indeed rings that are not polynomial rings. We've already seen in some examples before how we can create elements of the ring. Here's a new way. We can call directly a function called ring_lm. We then say the ring that we want the element to be in, and then we give, if you like, the value as an expression, but inside a string. It has to be inside a string because alpha and beta are probably not known. There'll be variables with unknown values or undeclared variables, and without making it a string, CoCoA would then complain. It would try to evaluate it, but that wouldn't work. So we have to put it in as a string. So here we are. So we've not chosen P2 as the current ring, but we're able to evaluate an element of that polynomial ring directly by using the ring_lm function. Of course, we've seen before that we can do the use command, and that then would set P2 as the current ring. And now we can type in the expression directly without making it a string. Get the same answer. That's no big surprise. Now we created 4 rings earlier on. Two of the rings had both x and y as indeterminates. But if I try to evaluate x and y now, CoCoA will complain, saying, in this case, it tried to evaluate one of x and y first. In this case, it tried to evaluate y first. And then it says, cannot find a variable named y in scope. So y has no value, and it complains. Because we've not chosen P3 or P4 as the current ring. And CoCoA couldn't guess which one we might want. So it doesn't attempt to guess. You have to say explicitly what you want. So it's just a little bit about rings. Ring homomorphisms. Again, we've seen something about this before. So quite a useful function is canonical hom. So if there is a canonical homomorphism from one ring to another, then canonical hom is generally able to build it for you. It's not perfect, but it works in many cases. And it can be useful if you want to move a value from one ring to another one. Actually, I think that was meant to be, in some sense, without really transforming it. Because we've seen before that ring homomorphisms can do quite general transformations. So let's have a quick look at an example here. So P3 is the ring ZXY. We'll just recall that. So let's create an element of it. In this case, it's just happens to be an integer, but it's now represented as a polynomial in that polynomial ring. Printed out, it appears to be an integer. We can ask for the ring it belongs to. Oh, sorry, I was misreading carefully. Sorry, we created this as an element in the ring Z. So this is an integer belonging to the ring Z, and its ring is now Z. Now we can then get a canonical homomorphism to embed the ring Z into P3, that is Z of xy. So that'll simply embed Z as, if you like, the coefficient subring inside P3. So phi is now a canonical HOM that embeds Z into P3. We can then apply that to A. Well, result prints out the same, still looks the same, 123. But if we ask for its ring, we now see that it's an element of the polynomial ring. We've seen this before. Since they belong to two different polynomial rings, two different rings, we're not allowed to compare them for equality. CoCoA will give an error saying that they should be need to be in the same ring, but they weren't. So that's a very simple example of canonical HOM. It's a bit more flexible than that. Let's have a look here. So creating a new ring homomorphism with polyalgebra HOM. So polyalgebra HOM works only if the coefficient rings are the same, and then the coefficients are mapped essentially by an identity. Right, so we now use P3 as current ring, and we create a list of images of indeterminates. So this is now a list of values, and they're going to be in the codomain. Now in this case, I'm going to create a polyalgebra HOM from the ring P3 into the ring P3, and it will map the first indeterminate, that's X, it'll map it into the first element of this list here. It'll map the second indeterminate to the second one. So we can do that. Now we can, so here is an element of, so we have both domain and codomain of the same ring here. We can now apply this polyalgebra HOM to an element, that particular element we've just seen. Actually, okay, this element doesn't even involve Y, so not terribly exciting. But we see that it mapped each X to an X squared, which is what we expected. If there had been some Y's in here, that would have been mapped to a Y cubed. We've seen before that a couple of inspectors for ring homomorphisms. We can ask for the domain and the codomain. So we already know in this case they're both the same. There is no direct way to get the images out of it. So there's a quick exercise for you. How could you write a function to get a list of images from a given ring homomorphism? That's just a little exercise. So here's another way of creating a ring homomorphism. This time we're going to use PolyRing HOM. You might start to wonder, what's the difference between polyalgebra HOM and PolyRing HOM? So they are quite similar, but the main difference is polyalgebra HOM assumed that the coefficient rings were the same, and that coefficients would be mapped by an identity homomorphism, so that they wouldn't be changed. Here we now, the coefficient rings don't have to be the same, and we have to specify how they're going to be mapped. So we'll take two rings here. We'll have, let's say, P3, which is Z of xy. We've already seen that. And we'll take P2, which is a bit different. So that its coefficient domain is now the field of 31 elements, finite field of 31 elements, and its indeterminates called alpha and beta. So building a ring homomorphism with PolyRing HOM involves a little more work. We have to say what what ring homomorphism we want to use for the coefficients. So in this case, I'll use canonical HOM from the coefficient ring of P3, which is just Z, to the coefficient ring of P2, which is Z modulo 31. So we create that and we see what coef ring HOM built. So here it is. So we know it's in fact just going to be a reduction modulo 31. CoCoA prints it out as a ring HOM from Z to Z modulo 31, and the description of it is just canonical quotient. Now we know how to map the coefficients. We can actually build the homomorphism. As before, we need to have a list of images of the indeterminates in the codomain. So our codomain is going to be P2. So here we create a list of, clicked the wrong thing here. List of indeterminates. The first element is just going to be alpha in P2, and the second one is beta in P2. So we send that to CoCoA. So that's our list. Finally, we can build the PolyRing HOM here. So this is a polyring HOM from P3 to P2, mapping the coefficients according to CoF ring HOM. That we know it's just reduction modulo 31. And then mapping the indeterminates of P3 according to this list, images of indets that we just defined above. So defined it, and here's how it prints out with CoCoA. So it says it goes from this ring to this ring, and how it maps the indeterminate. So X goes to alpha and Y goes to beta. That's just to help us understand what it's doing. We can now apply it. So here's an element of P3. Looks a bit big and complicated. When we reduce it, when we map it into P2, it turns out to be much simpler. And we find, in fact, it's just alpha to the power 31 minus 2 times beta to the power 31. In fact, we could have known that because we know the characteristic was 31 in the ring, and being a homomorphism, we could map just the one factor in the middle and take the 31st power, and we get this. So there's no big surprise there. So that's all I wanted to say in this video. I went through a bit quickly, just a quick overview of various things that I think we can find useful. Well, I think you can find useful. So perhaps I'll just jump back to the top for a moment. So we've looked at power products, polynomial rings, and different ways of making ring homomorphisms.